All right, so we're going to be talking about the oxygen-hemoglobin dissociation curve, which looks like this, and how to interpret this curve, what it means, and various factors that might alter this curve. But before we do that, let's talk about the structure of hemoglobin, which is the globular protein that acts as the primary vehicle in blood for transporting oxygen from the lungs to the tissues throughout the body. So oxygen can also be carried in dissolved form in the plasma part of blood, but this is to a much lesser extent when compared to the amount of oxygen carried by hemoglobin. So as I said, hemoglobin is this globular protein, and there are sort of 4 seats for oxygen molecules on every molecule of hemoglobin. And as each oxygen molecule takes up a seat on this hemoglobin, the likelihood that another oxygen molecule will bind increases. In other words, the affinity of hemoglobin for oxygen increases as each subsequent oxygen molecule binds. And this phenomenon is called positive cooperativity. And this is what actually gives the oxygen-hemoglobin dissociation curve its sigmoidal shape here. And then once a hemoglobin molecule has been bound full to capacity with 4 different oxygen molecules, we say that it is saturated. So taking a look at the graph here, the oxygen-hemoglobin dissociation curve plots the proportion of hemoglobin in its saturated form on the y-axis, which is a percentage, and then the partial pressure of oxygen on the x-axis. So basically this curve helps us to understand how the hemoglobin in blood carries and releases oxygen. So the amount of oxygen bound to hemoglobin at any time, and thus the percent saturation of hemoglobin, is related to the partial pressure of oxygen in blood. So the plateau portion of this curve is the range that exists in the pulmonary capillaries in the lungs. So where the partial pressure of oxygen is high in the lungs, oxygen binds very readily to hemoglobin, so you're going to find it highly saturated. So the steep portion of the curve is the range that exists in the systemic capillaries of the tissues. And this makes sense because as the partial pressure of oxygen drops, as you get to the systemic capillaries in the tissues, there is a release of large amounts of oxygen for the metabolically active cells. Now, the partial pressure of oxygen in the blood at which the hemoglobin is around 50% saturated is typically around 26.6 millimeters of mercury for a healthy person. And this point in the graph is known as the P50. Now, in the presence of disease or other conditions, hemoglobin's affinity for oxygen can change, and this consequently shifts the curve to the right or the left and changes P50 accordingly. So when the curve shifts to the right, there is a decreased affinity of hemoglobin for oxygen, and this facilitates unloading of oxygen to the surrounding tissues. And vice versa for when the curve shifts to the left, there is an increased affinity of hemoglobin for oxygen. Now, what factors lead to a rightward shift or a decrease in affinity of hemoglobin for oxygen? Those factors would be an increase in carbon dioxide, an increase in acidity of the blood, an increase in 2,3-bisphosphoglycerate or 2,3-diphosphoglycerate, which I'll just abbreviate as 2,3-BPG or 2,3-DPG, an increase in exercise levels, or an increase in temperature. And if you think about it, all of these factors move the oxygen-hemoglobin dissociation curve to the right because these are physiological states where tissues need more oxygen. So, for example, during exercise, muscles have a higher metabolic rate and consequently need more oxygen. This also produces more carbon dioxide and lactic acid, as well as an increase in temperature, and therefore all of these things are tied together to facilitate oxygen unloading. Now, a decrease in all of these factors causes the leftward shift in the oxygen-hemoglobin dissociation curve. And there's a little mnemonic that is helpful for remembering whether an increase in these factors creates a rightward shift or a leftward shift. And that mnemonic is cadet face right. So the C standing for carbon dioxide, A for acidity, D for DPG, E for exercise, and T for temperature. And so an increase in these factors creates a rightward shift. And don't forget that ultimately a right shift means lower oxygen affinity, and a leftward shift means there is increased oxygen affinity.